Have you ever stopped to think about the magic that happens when you say, "Hey Siri," or "Okay Google"? I mean, your device is just sitting there, silent, all day, and then bam, it springs to life. How in the world does it pick out just those specific words from hours of background noise and chatter? Well, that's exactly what we're going to break down today.
So you gotta wonder, right? If it can hear, "Okay, Google," it must be listening constantly. So why bother with a special phrase at all? Why can't it just, process everything we say all the time? Turns out there are two really good reasons for that.
It all comes down to two huge things. First off, constantly processing and sending every sound you make to the cloud, your battery would be toast in an hour and your phone would slow to a crawl. And second, maybe even more important, it would be a massive privacy nightmare. So that wake word, it acts like a gatekeeper. It basically tells the device, okay, listen up, the next part is for you.
And that brings us to the hero of our story, the wake word. It's just such a clever and elegant solution to a really complex problem. It lets our devices be helpful without being totally invasive or draining all our power. But how does it actually work, on a technical level?
Okay, let's get specific. Let's say we want our wake word to be Python. How does a machine, a hunk of silicon and code, learn to recognize the unique sound of that one word and ignore everything else? The TV in the background, the traffic outside, other people talking. To get that, we have to start with the sound itself.
So, where does this all begin? Well, before a computer could even think about analyzing your voice, it has to translate it from a physical sound wave in the air into a language it actually understands, digital data. This first step is the absolute foundation for everything that comes next.
This whole translation happens in basically three stages. First, you speak, which creates an analog sound wave. Simple enough. Then, your device's microphone takes thousands of little measurements or samples of that wave every single second. But here's the thing, one tiny sample is pretty meaningless on its own. So the system groups them into small, overlapping chunks called frames. And these frames are just long enough to start finding some really meaningful patterns.
Okay, so we've got our sound chopped up into these digital frames. Now what? Well, now the real detective work begins. The first place we look for clues is in what's called the time domain. Now that sounds fancy, but it just means we're looking at how the sound changes over time.
Audio analysis really splits into two main approaches. You've got the time domain, which we're going to look at first. That's all about rhythm, volume, and energy. And then you have the frequency domain, which we'll get to in a sec, and that's all about the actual tones and pitches that make up the sound. The easiest way to think about it, it's like rhythm versus melody.
Let's start with this really clever little feature called the Zero Crossing Rate, or ZCR for short. It sounds super technical, but the idea behind it is incredibly simple. It just counts how many times the sound wave crosses that center zero line, switching from positive to negative. That's it. It's basically just a measure of how fast the sound is vibrating.
And why is this simple count so useful? Well, think about it. A high-frequency sound, like the s in the word hiss, or even just some background static, is going to cross that line a ton, so it'll have a really high ZCR. But a low, rumbly vowel sound, like the ooh in boom, will have a really low ZCR. Right away, this one simple number gives the machine its very first clue to help separate speech from random noise.
All right, so we've looked at the rhythm of the sound. Now let's dig into its actual composition. We're moving over to the frequency domain now, where we're going to break the sound down into its basic tones and pitches to find even more detailed clues.
This is probably my favorite analogy for this whole process. See, a sound wave isn't just one pure tone. It's a messy mix of a bunch of different frequencies, kind of like how a guitar chord is a mix of different notes all played at once. There's this incredible mathematical tool called the Fourier transform that lets the computer basically unmix the sound and see every single frequency, every single note that's hiding inside.
So once we've broken the sound down into all its individual frequencies, we can calculate something called the spectral centroid. This is basically the sound's center of mass, but for pitch. It gives us a single number that tells us, on average, if the sound is generally high-pitched or low-pitched.
And this gives the machine another fantastic way to categorize what it's hearing. A sound like hiss, which is just packed with high-frequency energy, is considered a bright sound, so it gets a high spectral centroid. On the other hand, a word like boom, which is mostly low-frequency energy, is a dark sound, so it gets a low spectral centroid. So we've got all these features, ZCR, spectral centroid, and a bunch of others. But right now, they're all just numbers.
how do we actually put them all together to teach a machine to recognize one specific word? This, my friends, is where the real magic of machine learning comes into play.
This leads us to a really, really important question. I mean, we can extract all this data, but our own ears are just incredibly sophisticated. We don't even have to think about it. We just naturally focus on the frequencies that are most important for speech. Can we teach a computer to do the same thing? The answer, incredibly, is yes, and it's thanks to a very special kind of feature.
And that brings us to the secret sauce of all of this. These things called MFCCs. That's a mouthful, I know. But what makes them so special is that they are a way of processing all those sound frequencies to specifically mimic how the human ear actually perceives sound.
So why does that matter so much? Well, our ears aren't equally sensitive to all pitches. We are naturally tuned to hear the middle frequencies the best, because evolutionarily, that's where most of the important information in human speech is found. MFCs let the computer do the exact same thing, pay way more attention to those critical speech frequencies, and kind of ignore the super high or super low ones.
By processing the sound in this human-like way, the MFCCs manage to distill a really complex audio chunk down to a small, simple set of numbers, a unique digital fingerprint that represents that specific sound just as a human would hear it.
So, how do we use these fingerprints? Well, the training plan is surprisingly simple. Step 1, you collect a bunch of data. In one project, a developer literally just recorded himself saying our wake word, Python, 100 times. Step 2, he calculated the MFCC fingerprint for every single one of those recordings. And finally, step 3, he fed all of those fingerprints into a machine learning model, basically teaching it, this very specific pattern, this is what Python sounds like. Learn it.
And the result? It's pretty amazing. On the developer's test data, the model achieved 100% accuracy. It learned to perfectly distinguish the Python fingerprint from all the other sounds it was given. It's just a powerful demonstration of how incredibly effective this whole technique is.
And this really gets to the heart of it. The final wake word detector isn't understanding English. It doesn't know what the word Python means. It's just a highly specialized pattern matcher. It has one job, and one job only, to listen constantly for that very specific audio fingerprint to show up in the sound coming from the microphone.
So let's just quickly recap that entire journey from sound to signal. It starts with your voice, which gets digitized into little frames of data. Then the machine extracts key features for rhythm and pitch. Next, it uses those amazing MFCCs to create a unique audio fingerprint that's based on human hearing. And finally, a model is trained to do one thing and one thing only: spot that specific fingerprint in the wild.
It is just incredible to think that from this one single process, a whole new way of interacting with our technology was born. And it all starts with just hearing a single word, which leaves us with a pretty fascinating question to ponder. Now that our devices can listen for a cue, what's the next, more complicated thing we should teach them to truly understand?